So basically I'm talking about computation jockey. This is an idea. I presented 2 previous years on it. And a lot of times when you're using Mathematica and such, a lot of times you're trying to kernel, you have to abort the kernel, it's freezing, a lot of the time, and you're like, just waste, it depends on how fast the computer is probably. But I know when you go to see a DJ, and they're mixing, started in the 70s with like disco and hip hop and everything. The DJ will go from one track to another, but they never drop the beat. They never say, "Oh, I got to abort the kernel, guys. Just wait a minute." You know what I mean? They just hang out on the dance floor here, studio, studio wherever. And so anyway, I thought, why can't we do the same thing with computation? Especially when you're teaching a class. Being a teacher, I know a lot of times the kids will be all ready to learn. You got 30 minutes, and then the teacher says, let me find my PDF, and then they're like bending over looking for the PDF for like 2 minutes, and then they said, let me find that at an MOV file, and then they're looking for the MOV file. By the time they'd probably find 3 files, their computers crashed, they've looked for everything in all their folders. I thought, why can't you DJ a lesson? And that was one idea, DJ a lesson, but why can't you also then I thought, why can't you, so you could, on these buttons, normally when you have a DJ, they press a button and say, flavor, or something, when they press the different samples. I wanted it to be like you load your PDF, and then, you can scratch and do like when you go, when you push it up, the PDF will go, one page forward. You do a back scratch, the PDF will go 1 backwards, and then you can, mix, go from your PDF to your MOV, and then go to a simulation. And I basically started developing this idea more. I thought, why can't we just make an interactive, take all the mathematics? That's what brought me to Wolfram, and the stack that they're building, is that basically they try to treat all data types, and data is first-class systems that are, all interconnected and equivalent. So these are just some of the previous talks I did the last 2 years. I was showing different things. I was using a chaos pad to control XY grids, and basically just talking about different years. So we were supposed to be showing this on MyWave. The Bluetooth is just a pain. I'm just going to take it off, but unfortunately we weren't able to get that. That was a major part, but the Bluetooth just wasn't working. This is probably what I'll show later, but so today, would you like to have any volunteer? Anybody want to be do you want to be a volunteer? Or anybody want to come up? We basically need someone to do it, so. Anyone want to you want to volunteer? All right, so. Here we go. So I'm switching the picture. Just do a regular one. That looks pretty normal, right? So. Yeah, we're not really exactly going to be scratched. Hey, it is changing blue. So if you see it changing blue.
See, it's when you put it on its head, it stops.
Yeah, I'm brain dead probably. So that blue color, at least something is changing. That's a proof of concept, thanks to Todd Gailey. We made it flash blue based on our thoughts. But in the future, what I want to be is pulling the Mandelbrot set, take the fractal dimension, z to the 2, all the way to z to the 8th, and map my EEG frequencies. And then I even want to try and trigger, I could maybe, in my mind, I think, and that loads, rule 30, think, in my mind. It just, puts out y to the second plus 3 or something. I was and pulling scalars and everything with my mind. So this blue, this is when they looked at the moon before they went to the moon, basically. This is all right, so as you can see, we have these controls. This is a standard DJ mixer. And you see these are the different rules of Stephen Wolfram's elementary CA. So see the size can be changed on there. Let's see. Let's make it a little bigger. So as you can see, you can control it. So basically, we mapped the first 127 elementary CAs onto the board. So we basically want kids to be able to have, like we have the EEG, they could have the control boards and interface. I did, in one of my previous talks last year, we showed how we can take CAs and fractals and put them in one interactive environment. I want to take anything from computational sciences and mathematics and put them together. Did you want to just play with this? I know it's like kind of simple for you, but.
You're talking to me, right? What am I supposed to do?
I guess you can just play with the CA. And actually, why don't you press number 1? When he presses number 1, look, it's a Julia set now. So actually, he's maybe just do 1 and 2 because those change that. Sorry, these two.
Who's running this?
Sorry. So this is actually changing the imaginary and real coordinates. So you saw by pressing a button, we went from fractals, or we went from CAs to fractals. And that inner part was supposed to be changing based on the EEG. So now I'm going to put on a little bit of effects. This looks normal. I know when he came in, it looked all trippy. So I'm going to put on some feedback effect. Let's see. See? So, and then you see what I'm saying? You can do something like kind of wicked with it, like. Yeah, so I'm doing a little bit extra stuff here, like. You see, this is just analog, so I want to be able to do the signal processing, like the visualization and Shadi's team and everything, and all the colorization. See, this is external. I want to be able to do stuff like that, but then pull it out in stereoscopy. So, I mean, you can see, it looks kind of weird, but you can kind of see what I'm trying to do. So I'm doing keying, basically. See, we got the keying there. And let's see, one more. If we so basically I think something might have gotten unplugged. Okay, so let me go to another slide. So, oh, here we are. Just I have to figure out why. Okay, music. There is some weirdness going on with it, but you can kind of see, like, in the future, we could be pulling it all out and getting it as funky as we see. It looks kind of like smoke, right? Looks like digital smoke. And seeing. See how it's sort of layering? It's like, I don't know. You can kind of get what I'm saying. I know I've been doing this for a minute. So let's go to the other side. Thank you, Todd.
I'm available for parties.
So now we go back to the slides. And so these were just some of the things I was using to get the feedback and all that. And basically, in the future, we want to have it on full IMAX. So what I looked up with, I was talking to NVIDIA and IMAX, and they're actually interested in, both of them are interested in partnering with Wolfram. And we want to, I looked it up with GPU and high-performance CPUs and such, it's 100% possible to do it. Have a kid have all these stuff. They could be in front of the IMAX, like when they make those movies for Marvel and Black Panther and all that. They all cost hundreds of millions of dollars, but a kid could just have an Arduino. As long as you had the GPU and CPU unit there in the IMAX theater, they could just bring their laptop and plug it in, and I think we could just have plug and play with Raspberry Pi and such, and they could be using pots, potentiometers, or DJ controls. And I'm thinking like you could give them something like exoplanets. They could be getting data from somewhere. They could get particle physics, getting something from Kaggle, and be parsing these large data sets and make a artistic show. We just had a simple Julia set with feedback, but what I want it to be is like, and then they could play on it too. They could take a fractal, shoot it into a CA, and I want to take all data types. Like let's say you had a curve based on a 3D plot of a function. You could drag in a GIF and put it on and map it onto the surface. Then you could have little matrix operators, and you could be dragging, and they could be doing linear algebra. You could have links to all of your Wolfram documentation, so they could actually be playing with it and reading the documentation at once. Let's say they're getting something from Riemann, and they're using like a Riemann sphere or something. Then they could look at the lineage of mathematics lineage pages that they got, and while they're playing and experimenting with anything in a computational field with no lag. So what's the last part? Everyone has their own opinions. Whenever you have a like you vote for somebody, like when they voted for President Trump and Hillary, some people wanted Hillary, some people wanted Trump. It's just like Pepsi and Coke, you know what I mean? Like people want their different things. So in a democracy, but in democracy, the people, like let's say there was like 3 people wanted to kill another person. That's democracy, right? You could be like, well, we just don't like that person, just like cut their head off or something. So sometimes democracy might not be fair to the little guy, right? So maybe everyone can have their own universe. So basically, could we like press a button, like how I was loading different samples, and like you're watching TV, Trump's president, you just press a button, now Hillary is president. But I'm not saying in a simulation, unless you treat the universe as a simulation, you press another button, Kool-Aid Man. Hey, like, we got to get fiscal responsibility or something, like, Felix the cat, you know what I mean? Or we could have, Wolfram could be president, or we could change Wolfram's skin green. We could take George Clinton and Stephen Wolfram and mix them, like, DNA-wise into, like, one creature and, like, put, like, 15 of them just, like, in space-time. That's what I want my end goal to be, to DJ anything in space-time. Like let's say you're at a party, and you have 50 people. You can be having a slider, like to the left, 50 of them are Chinese. To the right, 50 of them are Afro-American. You go to the middle, 25 and 25. You're just DJing, in space and time, your party. So could we do that? I came up with an axiom system to just kind of test it. So I'm not really like a teacher and an artist, so I'm not very skilled in coming up with axiom systems for first principles of mathematics and cosmology. But basically, I just posit this 7 axiom group. So could it be that the grand unified field theory, the fundamental replicator of like the universe, the CA recursive function, the fractal recursive function, and a primal feedback system? We got Einstein, Darwin, Wolfram, Mandelbrot, Norbert Wiener. Maybe it's all one formula. And this is what I posit it is, basically, based on these 7 axioms. So my goal now is to formalize these 7 axioms, because I think I just believe that they give a formal binary decomposition of the universe. And it might sound weird, but I really do believe it. And you can get the notebook if you want to look at it. I'm trying to take 7 axioms I defined in human language and convert them into the logical language Stephen was talking about. This is a variation on a model with optional 7 axiom, but with this decomposition, I actually can generate Pascal's triangle, which with just items from that from the axiom system, and so that from what comes out of it. And actually there's a polynomial description too I forgot to include. Here's just some drawings. This is basically about the statistic that I think is non-trivial, which is key to the axiomatic scheme. So basically, it has something called, everyone knows about self-similarity, but I have an axiom called self-similarity, CLL/F. And basically, like that's, I'm just positing it. If you think it's BS, you can try and test it, or write to me. And basically, if that's all. Anybody have any questions? Yeah. I guess I can go over them. So, and I'm going to say I'm in human language. So just this is just my attempt, as an artist and teacher to try and come up with an idea. So basically, the universe exists. So you just posit the universe exists, and that it has enough variation, that we're trying to basically just generate. So basically, that the universe exists, we can say that. The number two, that it has a finite beginning. So we're working with a discrete system. So already, people might have a problem with that if they think the universe is completely continuous in its nature. Three is that we take the Euclid's definition of a line segment. So this is describing in human language, but basically I'm trying to, formalize these and look at them in my next year. So basically, did a fundamental recursive operation. I know some people might think, with relativistic time and all that there might not be, an absolute time, but at least it's this recursive function. And that space, so axiom 5 is that there's a statistic to space, which is basically what's described in this image, where I count, I take, at each step, basically, I found a statistic that in dimension 1 on the line segment holds to hypercubes. And the reason I looked at hypercubes is because only hypercubes can tile absolutely, can only regularly. Like if you take tetrahedron, you can't tile with regular tetrahedra at all dimensions and fill the plane for lattices. And so basically, I was looking at a series of hypercube recurring on itself. So in dimension 0, it would actually be a point. So this is just kind of like wild thinking, but maybe the Big Bang had two states. Not a Big Bang, but it's the primal singularity and point at the beginning of the universe had two states, 0 and 1, and we happen to use it as 1 as a seed to generate our universe. And so so I count whether a seed is active. Like here we got a line segment. It's actually composed of line segments. That's a self-similarity, CLL''F. And so like in the middle, it's active. It's touching 2 active neighbors, whereas on the right side, because it's active only touching 1 active neighbor, add it all up, you get 7, and the extra energy, why it's not, the extra statistics, why it's not 9, they're actually displaced to the outer part, whereas here you can see it's 49 on the inside. This is active, touching 2 neighbors through edges, touching 1 neighbor through a vertex, and see how you've got, and like in dimension 2, you've got 4 4s, 4 6s, and 1 9. That's actually shown by this picture here. You got 4 4s, 4 6s, and 1 9. So this picture goes up to 7 dimensions for the hypercube. And basically, I think we would have, take the Planck time, the number of, or possibly, if you think Planck time is the smallest unit of time, you'd have the Planck time number of recursions, and we'd be in a hypercubic structure that is of dimension to Planck time from beginning of the universe to now, and we'd be composed of cells that are similar to the overall structure of that. And that's how I hope to make Kool-Aid Man president by the next couple years. All right. So, any questions? Yeah. Yeah, I can show you. I'll show you one video. So let me switch. This will be one last video, I guess, to show you some stuff in action. I wasn't going to show this to you, but since Todd was requesting it. So this is me. This is a video I made internally for Wolfram with a friend of mine. see, we're launching CAs. This is Rule 30.
Did you have a musical performance?
Not here. Yeah, I mean, I could just do something unique, but it's not related to computation exactly. Like, and that energy I want to put into continuing these projects. So everybody have a good day. As you can see, I'm moving my finger on there, and it's actually moving the Julius site coordinates in real time with OpenGL. I didn't bring OpenGL this time because I presented it last time, just because I'm trying to build and I'm stepping on the foot pedal and changing the function. So now this is a new function, and you see I'm changing the complex coordinates with the x and y, changing the imaginary and real seeds, as well as launching CAs on the same thing. So thanks. Have a good day.